one-dimensional motion, 1D motion. This is what we've been working with, and what we have done so far is we've come up with 4 or 5 equations. Well, we've defined the velocity to be the displacement over the time, and we've defined average acceleration in a similar way. The change in velocity over the change in time, right? So we have delta x over delta t, and then delta v over delta t. Average velocity, average acceleration, and then we played around with a few things and came up with 4 equations. Delta x equals half vi plus vf times delta t, and delta x equals vi delta t plus half a delta t squared. And we also had vf equals vi plus a delta t, and we had vf squared equals vi squared plus 2a delta x. And this is what we labeled, what we called as the call this equations of motion. Now all of this was derived using algebra, and all of this runs off of the concept of average acceleration here, and acceleration as defined as such. However, these only work for the case where acceleration is not changing with time. So you can use these equations, all of these here, you can use them as long as acceleration is constant. I'm going to put here a is constant. And now it's fairly easy to see why that's the case. So what I'm going to do is I'm going to rewrite this equation as follows. Delta x, that's xf minus xi equals, well, actually that's not the one. I don't want to do this one, so let me get rid of that. And for that matter, let's just get rid of this section here so we have a clean board. So that goes away. So what I want to do is I want to take this equation and let's rewrite it. This is the same thing as xf minus xi equals vi delta t plus half a delta t squared. Now I'm going to take this equation and let's see if I can do what I want to do. What is it that I want to do? I think this is what I want to do. That's not what I want to do. Something happened. Not quite what I wanted. There's something else. Hang on. Oh, I think I know what I have to do. So I want to take this equation. Not quite that. I want to take all of it. And there we go. And I want to move it on the top. I'm going to rewrite it a bit. I'm going to write this a little differently. So I see what I have to do. No. Okay. So if you look at that, let's rearrange it one more time into xf equals xi plus vi t plus half a t squared. So instead of writing delta t, I just wrote t, and that's fine. I brought xi to the right hand side and I left xf here. Now what I can do is xf is the final position, but the final position varies with time. If I let the time run, xf continues to increase or decrease depending on what's happening. So what I can do is I can write x as a function of time, where this is my, just going to say this is my xf, right? And so from here what I get is that equation becomes x as a function of time equals xi initial position, which is a constant, because that's just sort of your starting point. Your starting point doesn't vary, it's just where you started. It's a number, plus vi, which is also a constant, times the time plus half a t squared. Now this is a position function. So let's take the derivative of this and see what we get. So dx dt equals, Now, the derivative of a constant, I guess I should probably just do this d dt of this whole expression, xi plus vi t plus half a t squared. So once we take the derivative of this whole expression, d dt of xi, well, this is a constant, right? This thing here, it's this is a constant. This is a constant. Well, a constant as well. Anyways, there's that. And what we get out of it after taking the derivative of this whole expression is we get, well, the derivative of a constant is just 0, so that goes away. This simply gives me vi plus a t. That's what I have. And that, of course, amounts to nothing else but v, the function that expresses velocity as it varies with time. And of course, this is just what we've done in the past. If we call this vi plus at equals vf. So these two equations are the same thing, but we can get there with derivatives as well. Then what we can do is we can take the vdt equals, let's just take the derivative of this. So derivative with respect to time of vi plus at. What we end up here with is, we take the derivative of this expression is just a. A is the only thing left. A is a constant. This whole process here. So you can take one of these equations. You can take this equation here. You can rearrange it such that you determine what is a variable, such as this and the time, and what are the constants, and then you can work towards, you can go from the position function to the velocity function, which is this step, and then from velocity function to the acceleration function, which is this step. And you end up with the same stuff as what you had before, right? Because what we've shown is that from here, you can move to here. You can also work backwards, if you will, and it's still all relying on constant acceleration. But if we say that a is just a, where this is a constant, so some kind of a constant, we can take antiderivatives of this, and we end up with, well, from the theory of calculus, we know that v is simply a dt, and so you could either put limits of the integration or not. It doesn't really matter. But so you end up with a, since a is a constant, times t plus some kind of a constant from the integration. So let's call it c for the moment. But then that c, it is easy to show that this c simply becomes the initial velocity. Now, in case you don't see it, here's what you could do. So now what we have is v as a function of time equals a times t plus c, and then do the following: take this function v and let t be 0, and that's going to give you c. Right? Well, because once you plug in 0 for t, you end up with nothing else but c. And this, of course, is also just vi, since vi is the initial velocity, and that's the velocity at time t equals t0. So what we have is that v as a function of time equals a times t plus vi, but this is nothing else than the equation you have seen before, which is vi plus at. So you can work by using integration, you can go from a to v. You can take another step, and you can go and take another antiderivative of this expression, so that you would have, from the theory of calculus, we know that the position function x as a function of time is just the antiderivative of v, the velocity function, dt. And you could put the limits here if you wanted to. You could go from 0 to some final time t, or you could just do this integration this way. And so we'd have vi plus at is the function for the velocity, dt. And now if you run this thing through, you end up with vi t plus half a t squared plus a constant from the integration c, so some kind of a c. Now, it's easy to show that c is just the initial position. So do the following: x, the function of time, set this time to be 0, and then what that will give you is, well, this term goes away. So you'd have, let me write this out. This is vi times 0 plus half a times 0 squared plus c, which it just gives you c. So c constant c is simply the position at time t0, but the position at time t0 is xi. And so now what we have is that the function of the position is the vit plus half a t squared plus xi. Or what we could do is x as a function of time. This is just a position at a specific time of interest. Then we could call that xf. And so then what we would have is xi plus vit plus half a t squared. And I think you see where I'm going with this. This is simply xf minus I equals vit plus half a t squared, and this just becomes delta x equals vit plus half a t squared. And this is the same equation as what we have gotten before, but using just algebra. So you can go from the velocity to the position using calculus, right? So there's that. So we could have derived, when we look at these equations here, these four equations, we could have derived this one and this one using calculus. This one, I mean, if you really tried, you probably could, but at some point it wouldn't just be calculus. And then, and this one, this is sort of, this comes out of algebra. This really also does come out of algebra, but just using calculus alone, you could easily show that this works and that this works. But all of this here, everything that we have done, relies on the concept of acceleration being constant. Which is not always the case. So if, well, first of all, if acceleration is constant, if you're solving a problem in physics about one-dimensional motion and you know that the acceleration is constant, just go for these equations and solve the problem using these equations. There is no need for you to start from the scratch, from the definition of acceleration, and or even from the fact that a is constant, and then start deriving using calculus, and then eventually getting the equations and then solving the problem. That's just a waste of time. So if you read the problem and you know that the acceleration is constant, what you should do is just go straight for these equations and then solve the problem using these equations. But now you know that you can derive them using algebra, but you can also derive the same equations using calculus, which is what I've shown you here. What happens though if acceleration is not constant? So if a is not constant, then none of the previous four equations works. You cannot use them. If a is non-constant, then this equation here, for example, vi delta t plus half a delta t squared, doesn't work. You can't use it. And the same thing for all the other equations. If a is not constant, you cannot use these equations. So if you know that acceleration is variable, then you kind of have to go from the basics and start deriving the expressions for velocity and position if you want to solve the problem. So suppose that the problem tells you that acceleration varies with time, such that a as a function of time becomes 2t minus 5. And then the problem goes on and states that this is what's happening, and this is what you have to solve for, and so on and so forth. So before you can solve a problem like that, you should probably first find an expression for the velocity as a function of time, which in this case, that's pretty easy. It's pretty easy to show that this would be squared over 2. So what I have is t squared minus 5t plus some constant c. And how did I get there? Well, going from this step to this step, you get there by noting that v is the antiderivative of a dt. And so take the antiderivative and you can confirm that you end up with the equation I have. Further, you can move on and get an expression for the position as a function of time. And so this would become Well, so I have c as a constant that carries over from the previous equation, but then I also end up with another constant. So what if I label this c1, c1, and then c2, here's another constant. Now how did I get this equation? By going from this one to this one via the route of integration. So what I had is x equals the antiderivative of v t. And you can confirm that this is what you get. All right, so if the problem gives me the expression for the acceleration, then I can very easily derive an expression for velocity and for the position. How do you determine the constants? I'm going to put here constants. Just set the function to 0. So rather not, well, set time to 0. So if I want to find, so let's maybe do c1. To find c1, what I would do is set the time 0, and then that gives me 0 squared minus 5 times 0 plus c1, and that's nothing but c1. So c1 is the velocity at time t equals 0, meaning c1 is just the initial velocity vi. For c2, I would do something similar. So what I would have is, but now I take this function here and I set time to be 0 again, and now what I have is 1/3 0 cubed minus 5/2 0 squared, and then plus, instead of c1 I can now write vi times 0 and then plus c2, and of course that gives me c2, which is c2 is the position at time t equals 0, and that of course is the initial position xi. So I could rewrite these equations if I wanted to, and instead of c1 I would put vi, and instead of c2 I would put xi. But anyways, that's that. Now the other way you could get these problems where acceleration is variable is by, I guess I could label this as A. Now here's B. So perhaps the problem, instead of giving you acceleration, gives you the position or velocity. Let's go with the position. So let's say that the position is given as t to the 4th minus 5t. And then the problem goes on and asks you about a bunch of questions. You would probably want to find an expression for v. And in this case, this would be 4t cubed minus 5. And how did I get there? Well, I took the derivative. So v is the derivative of the position with respect to time. And I could also get an acceleration expression for the acceleration, and that would just be 12t squared. That's it, 12t squared. How did I get there? I took the derivative. So a equals dv dt. Now I suppose I could get a third option where the problem says, so see the problem, perhaps the problem would do this, it would give me v. Right? So it'd give me v as a function of time, and it would say that v is maybe picking easy functions, but the point is to illustrate the idea here. So maybe this would be 2t squared plus t, and then asks a bunch of questions. So what I could do is I could find an expression for acceleration. That's a equals 4t plus 1. How did I get here? Through a derivative. dv dt is acceleration. And I could also find an expression for the position function. So x equals, x as a function of time equals 2/3 t cubed plus half t squared plus a constant. Right? How did I get there? Through integration. So maybe I'll move the screen a little. X is the antiderivative of v dt. All right, so that's the general outline of how you'd proceed if the acceleration is not constant, right? So if acceleration is not constant, then you really have no other choice but to use calculus and derive all of the equations that you would need. If acceleration is constant, then I mean, feel free to derive all the equations from the from the scratch. But why do that? Just go ahead for the result that we have, meaning these 4 equations of motion. All right, so that's sort of the outline of 1D motion, with acceleration being constant and non-constant. There are other types of problems where you can, I only gave you the case where the problem gives you an acceleration as it varies with time, but problem could give you an acceleration as it varies with position. That would be something a bit different. I don't think we're actually going to touch a problem like that. It's not a big deal, but it's just something, it's just a different, it's a variation on the same theme, but it's slightly different. What I'm going to do now is I'm going to solve, let's see, 1, 2, I'm going to solve 3 problems from the worksheet. And the worksheet is put up on a class on our class's homepage, so you can access it there. So this is the worksheet. 1D kinematics, calculus problems. There's only one worksheet with calculus that is within this unit, so we should be able to find it in the specific module for this unit. It should be easy to find it. So I'm going to solve, let me highlight the problems I'm going to solve. So what I'm going to do is numbers, what am I looking for? I'm looking for numbers 2 and 3 and 6. I'm not sure if I'm going to do all of what's in these problems, but that the idea is that I touch on these 3 problems and then the rest becomes yours. The rest becomes your homework. So let's start with number 2, second problem. Given the position function of a particle, so what I have is a position x as a function of time equals minus 2t cubed plus 5t squared minus 2. Find instantaneous velocity at 2 seconds. Okay, so part A, I need instantaneous velocity. Well, given that I have position function, I can very easily get to the velocity. Velocity is dx dt. And so in that case, this just becomes minus 6t squared plus 10t, and constant goes away, so there's that. But I'm looking for the instantaneous velocity at 2 seconds, so what I need is v at t equals 2 becomes minus 6 times 2 squared plus 10 times 2 equals, I think it's minus 4. Do I have units for this? I don't see units. We'll probably make up some units. Time is in seconds, but I don't see time for the position. Just say it's like meters. So meters per second is the instantaneous velocity at 2 seconds. Part B. So part B says instantaneous acceleration at 3 seconds. Okay, well, acceleration is dv dt. And so in this case, it becomes minus 12t plus 10. And I want acceleration at 3 seconds. So t equals 3. In that case, it's just minus 12 times 3 plus 10. That gives me 36, 10, 26, minus 26 meters per second squared. So that's the acceleration. That was easy. C, average velocity between 3 and 4 seconds. So this is going to be a little more work, I think. But what I'm looking for is the average velocity between 3 and 4 seconds. Well, here's the definition of the average velocity. Delta x over delta t, which amounts to final position minus initial position over the time interval. Now the final position we're talking about is 4 seconds. So x at 4 minus x at 3 divided by the time difference between 4 and 3, right? So 4 minus 3. This is what I need to, this is what I have to do. Find what this becomes. So I'm going to write this out as v at 4, that would be minus 6 times 4 squared plus 10 times 4, and then minus x at, oh no, I actually made an error here. See, I'm using the wrong equation. What I need is, so let's go back, get rid of this. Goes away. I was using the velocity equation, but what I should be using is the position equation. So position equation is this. It's minus 2 times t at 4. So this is 4 cubed plus and then 5 times 4 squared minus 2. That's the position at 4 seconds minus the 3 seconds. So 2 times 3 cubed plus 5 times 3 squared is 2. That all of this divided by the time interval, which is just 1 second. Everyone, and then I get whatever I get out of it. I just want to make sure that I don't make an error, so I'll take my time and I'll calculate this out. I'm actually not going to calculate this out, but you probably should. That will give me the average velocity between 4 and 3 seconds. Part D, average acceleration between 1 and 3 seconds. So the definition of average acceleration is delta V over delta T. And that means that I'm looking for V at 1 and 3, V at 3 minus V at 1 divided by the time interval, which is 3 minus 1. So let's plug in what we need to plug in for this. That becomes, I might be able to squeeze it here. A good idea, but maybe I can squeeze it here. The velocity at 3 seconds, that's where velocity somewhere up there. There it is. This is minus 6 times 3 squared plus 10 times 3. That was not a good idea. Minus, maybe I can squeeze it. Minus, so let's keep this thing in here. So open parentheses. Minus 6 times 1 squared plus 10 times 1. Was supposed to be 1, not a plus. And then all of this divided by 2 seconds, because that's the time interval. And then I calculate this out, and this, whatever I get out of it, this is what I would get for the average acceleration between 3 and 1 seconds. Wasn't there something else? Oh yeah, part E. So I'm looking at second problem here, part E. It's initial position, initial velocity, initial acceleration. Okay, so part E is easy. The initial position, if I go back to the equation, initial position is just 2. So the initial position xi is the same thing. This is the same thing as x at time t equals 0, and it's pretty straightforward to see that that's just minus 2. That's the initial position. The initial velocity, that's the velocity at time t equals 0. And looking at the equation for the velocity, there it is. That's 0. So the initial velocity is just 0. And then initial acceleration is the acceleration at time t equals 0. And so looking at the acceleration equation, that would just be 10. I should add units. I should really add units to this. So this is meters. This is meters per second, and then this is meters per second squared. All right, so that does it for the second problem. Now, problem number 3 says find maximum positive velocity of a particle. All right, so we can probably do this one here for number 3. Find maximum positive velocity of a particle. And that would be for this position function. So let's copy over the position function. That was negative 2t cubed plus 5t squared minus 2. Right, so this is the position function. And then problem 3 says, for this equation here, find maximum positive velocity of a particle. All right, so what I need to do is I need to find the velocity equation, v the function of time equals, and I already did that, but I guess I'll do it again. So this is minus 6t squared plus 10t. That's the velocity, and I'm looking for the maximum velocity of a particle. If I want to find the maximum value of a function, what I have to do is take the derivative of it and set it equal to 0. So the derivative of v respect to time, which is of course acceleration, that just becomes minus 12t plus 10. and then I have to set it to 0, set it equal to 0. And so that gives me minus 12t equals minus 10, which means 10 t is 10 over 12 or 5 over 6, but let's just keep 10 over 12. So at this time, the velocity is at its maximum. And this comes out of basic calculus theory. You want to find the maximum value of a function, you take the derivative of that function and set that derivative equal to 0. Reason being is that where the derivative of a function is 0, that's where the slope is 0, and slope is 0 flattens out at the peak of the function. So, and if this is news to you, if you've never seen that before, then at some point when I'm back, just ask me about it and I'll try to give you more of an explanation and maybe draw a graph on a board and show you how that works out in a visual. Or maybe I'll just do this. You know, if you have a function, the function looks like this. If you observe what happens to the slope, this is the function, and you just keep taking the derivative of a function. What you're doing is you're calculating the slope. Every time you take the derivative of a function, at a specific time, you calculate the slope of a tangent line here. So you're calculating the slope here, calculating the slope, calculating the slope. At a maximum, this would be local maximum. The slope is 0. And the slope is non-zero, 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 and then there's 0 again. This is local minimum, but the slope changes and changes. So what you're doing is you take the function, take the derivative of it. Derivative of a function is effectively slope of these tangent lines. And then when you set the slope to be 0, you're looking for this one. And then that allows you to find the time on which the slope is 0. And from here you can take it and finish off the problem. So what I have to do is from here, it follows that Vmax is V at t equals 10/12. So I plug that into my expression. I'm going to have minus 6 times 10/12 squared plus 10 times 10/12. And whatever I get out of this would be the maximum value of the function. This graph here, it does not correspond to the actual position function that we had here. Right? Just keep that in mind. I just drew a random sketch of some random function. But yeah, so maybe let's do that so I don't confuse you with this picture here. In any event, here's the maximum value of a function. Well, whatever that comes out to be, so I'd have to actually pull out the calculator and calculate it. But that's that. So that was number 3. And I should do number 6 as well because I have it there. Let me clean up the board. So for number 6, let an acceleration of a particle be a equals to t, and so on its initial velocity is such and such. So how about I set this up as a given? So the function for acceleration given to me as 2t. So it's not a constant acceleration, but it's a variable one. I also know that the initial velocity is -3 meters per second, and initial position is x equals 1 meter. So I'm going to put here xi equals 1 meter. Derive velocity and position equations, and then so on and so forth. So that's about it. And then the actual, that's all they give me. I guess in the given I can also do this. V as a function of time equals t squared plus a constant, but I know that this constant is just the initial velocity. And so in that case, it's just -3. So really what this becomes is t squared minus 3. I guess in case somebody got lost on this, maybe on the side I'll confirm that this is the case. So if I found that this function v is t squared plus c, And I know that, well, then what I can do is I can say v at t equals 0 squared plus c, which is just c. But v at t0, that's vi. So vi is c, and of course vi is simply -3, and so -3 meters per second is c, right? And so this is where I get this c becoming, this is where I get c becoming -3. All right, so there's that. Let's get rid of this. That's gone. And I can also easily derive an expression for the position. That would be 1/3 t cubed minus 3t plus, I should label that c1, plus c2, some constant c that comes out of the integration. Right, so I took from here to here, I did the antiderivative, and from here to here, I also did an antiderivative. That looks convoluted. I should probably get rid of all of that, but all right, let me do that. So this stuff now goes away. And let's figure out C2. So we have that done. So C2, that's just the initial position, and you can do the same little exercise I just did seconds ago. And so this becomes 1/3 t cubed minus 3t plus 1. So I have the 2. I have all the functions that I need. All right, so now for part A, find velocity at 2 seconds. That would just be v of at 2, which is 2 squared minus 3, and that just gives me 4 minus 3, 1 meter per second. I guess that's it. B, for part B, find position at 3 seconds. That just be x at 3. Of course, this simply becomes 1/3 times 3 times 3 times 3, that's 27, minus 3 times 3, and then plus 1. So what I have here is 9 minus 9, this is just 1, so 1 meter. And then C is find average acceleration between 2 and 3 seconds. So average, remember the definition for these averages is delta V over delta T. And that would imply I'm looking for the average between 2 and 3 seconds. So V at 3 minus V at 2 divided by 3 minus 2. And so plugging in expressions for what I have there, I would have 3 squared minus 3 minus 2 squared minus 3, and this divided by 1. So I'd have 9 minus 3, that's 6, minus 4 minus 3 is 1, and then this divided by 1, so that just gives me 5 meters per second squared is the average acceleration between 3 and 2 seconds. All right, so that's that for these problems that I was going to solve here. And none of this really should be a surprise to you, I think, assuming that you have taken calculus. And if you have not yet taken calculus and you are taking a calculus, then you should be okay. It's just that you're gonna have to get ahead of the class and your calculus class and learn basic derivatives and basic integrals, and you can come see me and I'll tell you which functions specifically you're gonna have to know how to differentiate and integrate. But that's that for this worksheet as far as I'm concerned. Now your homework becomes the rest of it. So I'm going to maybe in blue label what your homework is going to be. So at home, you will solve problems 1, 4, 5, 7, 8, 9, all of these problems become your homework. And I'm gonna set up a place in Canvas where you can submit that stuff. Probably make this homework due for the next class. So When do I see you on Thursday, I think. Yeah. All right, well, that does it for the lesson.